get started. Today is what, Wednesday? Good. So the plan today is not quite what the title slide says. Sorry, we're not going to talk about cross products so much. We're going to talk about balance and equilibrium. Okay? So before that, I'll just give an example about some stuff we did before. About rotational motion. And then we're going to get to the stuff that I just had memorized. Okay. So imagine you have a disk. So here's a disk. That's the center. And imagine that it's a nice disk. It's not whatever deformed shape that I just drew. And it has a moment of inertia around its center, which is given up there. So 3 kilograms times meters squared. Quick sanity check on the units. Remember, moments of inertia are like mass times distance squared, so this fits. Yeah? Okay. And so over here, it's accelerated from rest to 33 revolutions per second in some amount of time. So it goes from rest to 33 RPM in 2 seconds. Constant acceleration. And so, questions we could ask, right? So what's the torque that was acting on the disk during that time? And also, what is the initial angular velocity? And what is the final angular velocity? Things like that. Okay, I just want to show you how to work this kind of problem. You might know already, but just want to make sure that you see it. So the first thing to consider is to try to see, like, okay, if it's going at a constant acceleration in some amount of time, then you have to think, like, okay, what formulas could possibly be helpful to us in thinking about this problem? So we somehow want to relate velocities, accelerations, and time. And it's a spinning system, so it seems very reasonable that we're going to be interested in angular velocities and angular accelerations. And so then one formula that we have of this type is that the final angular velocity is equal to the initial angular velocity plus the acceleration times time, angular acceleration. Well, those are the concepts we got to link, so that's one kind of thing. And then another kind of thing is that if you know this quantity, the torque is the moment of inertia times the angular acceleration. So we can basically see that this is the kind of thing that we want. We want this, we want that. We know that, but we have no idea what this is. But we know that part too. So this one is what we're interested in. This is what we're interested in. This is what we're interested in. So we have the time. So we can use these equations to basically solve for everything we want. So let's see how that works. So the first thing, so if you're at rest, right, that means your angular velocity is 0. Does that make sense? So you start at rest. And then, what is 33 RPM? So that's some kind of angular velocity. But it's in an awkward set of units. So basically, 33 RPM is telling you that you are doing 33 revolutions every minute. And the way that we tend to work is we're interested in, radians per second. And instead, what we have is 33 revolutions per minute. And we want to convert this to radians per second. So the way to do that is to first say to ourselves, well, 1 minute is 60 seconds. then minutes will cancel, we'll get seconds. And 1 revolution is 2 pi radians. So multiplying this out, we will get the final velocity. So let's see, so this would be 33 times 2 pi divided by 60 radians per second. That's the final velocity. So there we go. We got this, we got that. So we can get the angular acceleration from this formula. The angular acceleration is the final velocity minus the initial velocity, which of course, I mean, this part is 0, divided by the time. So the time is what, 2 seconds? So if you divide this by 2, you just get rid of that 2. And so you'll get 33 times pi divided by 60 radians per second squared. So we have the angular acceleration. And finally, we could get the torque. So let's see. This thing was 3. So just multiply everything out and we'll get 3 times 33 times pi divided by 60. Kilogram meters squared radians per second squared. So this is our answer. So you could do this out with a calculator. Yes, go ahead.
You cancel out the 2, but you've got to, actually, it'd be 33 or 30.
Let's, hold on, let me think about it for a second. So I took this thing, and I divided it by 2.
Oh,
But then I killed this 2. And 60 stays around.
okay.
So that's this. I hope it's correct. Okay, so, I mean, I didn't do out the final arithmetic. You can do that better than me with a calculator. If you forced me, I would do this with another calculator, but it's kind of painful. So before I continue, do you have any questions? Okay. Yes, there's a question, sorry. Yes, of course, sorry, I was a little bit fast there. So the way I got the torque is I said, well, I know the acceleration now, and I know the moment of inertia because the problem statement gave it to me. If I multiply them together, that's the torque. This is like F equals ma, but for angular things. Does that help? And so this 3 here is this 3, and I multiply it with angular acceleration. Questions? Yes?
What happened to the 2 seconds that it took to reach?
Good. The 2 seconds got used right here because what we really had was this. Okay? And then I said, look, because without this thing is here. And so and this part is 0 anyway. So I divide by 2 seconds, but this 2 can cancel with that 2, and then I go from there. I'm so glad you asked. Okay, other questions? Okay. Very good. All right, well, I just wanted to start off with an example instead of theory from the very beginning. So all the same stuff, except actually plugged numbers. When I did it at home, you'll have access to these slides. Sorry. Initial angular velocity is 0. There's a misprint there. Sorry about that. Okay. So what I want to do from here is to talk about balance and then equilibrium. Okay? So it's a bunch of silly pictures of balance. So in physics, if you want to talk about systems in balance, what you really do is you use the fancy pants term for balance, which is static equilibrium. The image that you see here is what came up in a Google search when I searched for fancy pants, and that's what they showed me. Okay. What this means, okay, is that if a system is balanced, it's not moving, okay? So if we say that it's a static equilibrium to make it sound nice, what we mean is it's not rolling, it's not sliding, it's not rotating, it's just sitting there, right? But for it to like move, you need two things. If it were to move, there would be a net force acting on it. And if it were to rotate, there would be a net torque acting on it. And if both of those are zero, then at most it could move at constant velocity and angular velocity. But at least its velocity and angular velocity won't change. So to ensure that it's in equilibrium, you just have to make sure that the net force and torque are zero. Okay, so we're going to do examples of this. I should say, this is the part of the course that most people find hardest in this entire subject. I think it's because in this type of problem, everything you've learned so far suddenly comes together. No individual part of this is particularly hard, but it's just because so many things come together that I think people find it hard. So what I've laid out on this slide is kind of an algorithm for how to do these problems. It's too much to observe at once, so I'll just give you examples, basically for the rest of the day. So you start with a detailed label diagram, choose some axes, hopefully wisely, then decompose your forces along your chosen axes, and then impose that the net force must be zero. Because if not, it would move. And then you calculate the torques, and you find the net torque, it has to be zero. Now, your choice of axis can't possibly matter, because it's in your head, it's not physical, it's not nothing about the universe tells you where to put it, but making a good choice can make your life easier. I'll show you how in just a minute. And often, but not always, you'll discover that things like friction let you link horizontal and vertical forces, but that's really problem dependent. The important parts are from before. And the most important part is really the very beginning, okay? Draw a detailed label diagram and like choose your axes carefully and start decorating it with forces, and doing that actually gets you a long way through the problem. What? Something funny? 1 minute. Okay, and before I give you an actual example, just a reminder, if you have gravity in the problem, okay, the gravity pulls from the center of mass. Okay, in any problem where we're going to deal with equilibrium, that's the caveat here about gravity being, the force of gravity being the same everywhere is going to be true, and so this is going to work. Okay, so here's an example that I'm going to work, hopefully slowly enough that you can follow. Please slow me down with questions if there's anything that I say that you're not following. If you raise your hand and I didn't call on you, it's not because I'm ignoring you, it's because I'm being blind. Please just speak up, okay? Because I actually do want to address all the questions if I can. Okay. All right, so in this problem, we have a wall. And then there is a stick, okay? And then there is some kind of weight hanging from the stick here. That's a bad way of drawing it. Okay, and then there's a rope like this. And everything is in equilibrium. Okay? And the basic question that's going to be asked is, how much tension is there in the string over there? And here we should imagine that this is a pivot point. So this stick could move, okay? It could rotate if it was allowed to. So think of this as hanging up a sign from some stick, like maybe for an advertisement. Okay, so to actually work the problem, a bunch of stuff is happening in the slide. It's all going to get filled in nice and slowly on the board, so it's only up there so that you can oriented, we need to put in some assumptions, okay? So first, let me assume that the length of the stick is L, okay? And then let's say that the tension here is T. Okay, so T and that's what we're looking for. Okay? Okay, so now let me think for a second. What else do I want to do? So let's say that this thing has a mass m, and let's say that this distance from here to there is L over 2. Okay? So we want to figure out what's the tension. So the way to think about this is I'm interested in a situation where everything is stable. It's not moving. Okay? So that means the sum of the forces as a vector is 0, and sum of the torques is 0. In principle, also as a vector. Okay? But how do we do this more precisely? Well, so to make it more precise, let's pick the hinge as an axis. This is up to you. You can pick whatever you want. But if you pick the hinge as an axis, we can then take the stick and just draw it abstractly, forgetting that there's a wall at all. Okay? And let's see, what else do we want to assume? I mean, for simplicity, let's say that the mass of the stick is negligible. So it's basically 0. It can't really be 0, but let's say that it's small compared to the mass that's hanging from the stick. So it's a very light, very strong stick, and there's something heavy hanging from it. This is just to make the problem easier, and it's what's implicitly assumed in the slide. So we just draw the stick. There is a force coming off like that. That's the tension. There's a force pulling down like that. That's mg. This is the axis. And there is another force from the wall, like that. So let me call this the force of the wall. So far, so good? Okay. Okay. So then, let's try to figure out what we can say about the torques. So let's say that I make this direction positive. So that is, torques going that way are positive. Okay? Then, the torque, the net torque, is going to be mg, that's the force, times L over 2, that's this distance. Does that make sense? So up there, XCM is just L over 2. Okay? And then let's call this angle theta. So then the tension pulls up that way, so it's opposite to the force of gravity as a torque. And so we get tension times the length of the spring, length of the stick, times sine of the angle, indicated here. Is that okay so far? So actually, we immediately get something that we can say, which is that this whole thing has to be 0 if the thing is in equilibrium. But if it's 0, then you can cancel out the L's, and you can get an equation for t. So t, putting this term to this side and dividing by the sine, we will get mg divided by 2 sine theta. So we're almost there, we just don't know theta yet. So we need a little bit more information to get there. Any questions so far? Yes?
What's the force on the hinge?
Good, good. The force on the hinge is coming from the wall, because you see, this, I should have said something about it explicitly, sorry about that. So the stick is getting pushed into the wall by the fact that this tension is pulling up, right? So it's up and in, so the wall is gonna have to push out, at least a little bit. So that's this force. Now, I didn't consider it until I came out the torque, so why? The reason is that it's applied at the hinge, at the axis that I've chosen. And the distance from the point of rotation of this force to the axis that I'm using is 0. So if you write out torque is equal to force times distance times the angle, the distance is 0, so the torque is 0. So this doesn't contribute to the torque. It does contribute to the force balance, but it doesn't contribute to the torque. Does that make sense? Other questions? Yes?
So if the force from the wall is pointing inward, how do you know what direction inward is pointing?
You have to figure it out.
Oh.
Yeah, so it's not, I just drew it as some random direction. We'll have to deal with that later.
Okay.
Yeah. But to answer your question, it's going to be chosen such that the whole thing is stationary.
Okay.
So for consistency. Other questions so far? Yes?
So are you only gonna be really seeing torque on these type of problems at all, like just?
No, so force balance is also important. So I haven't gotten to that yet. But I just wanted to point out how torques come into it. So, let's see, how much I want to say about force balance. So let me just say a little bit about it here. So this was just to show you how torques can conspire to give you some conditions. If we wanted to consider force balance, what I would do is I would say, okay, so there is a, let's see, let me do it. Okay, so there's a tension this way with some angle theta. So that means that this force gives you something that goes up, and let's see, so it's this force. So that would be T sine theta. So I'm breaking up this force into something that goes up and something that goes sideways. So there's something that goes sideways here, it's T cosine theta. I'm going to do that for everybody consistently. So now from the hinge, there is something that is vertical, T wall vertical, and something that goes this way, T wall horizontal. I don't know what they are. But now I need to impose some conditions, right? So what I can say is that T wall vertical plus T sine theta. Oh, sorry, I'm not sure I'm calling it T. It's really just a force. It's not a tension at all. So that's confusing. Force. 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 Minus mg must be 0. This is the condition that vertical forces cancel. Right, I just added up all the vertical forces. And then force wall horizontal has to cancel against this guy. The horizontal part of the tension force. So you can see you're getting an equation that on the one hand, T is something that you know in terms of sine theta and mg, but you can now take that expression and plug it into these, and you'll be able to crank through the problem and relate different things to each other and eventually solve if you have enough time, or if I've designed the problem in a wise way that you don't have to do too many steps to get to what you need, if it's an exam problem. Does that make sense?
Yeah.
So eventually, again, just to reiterate, like you're gonna have to, in working these kinds of problems, put in torque balance and put in force balance and think about it. And like, get relations between things. And like, there are no new concepts involved in doing any of this. It's just applying the other things. It's just that there's several things happening at once, and so people tend to find this hard. But there's nothing really new about it. Okay. One thing that I should mention just before getting into other things is there can be all kinds of different types of equilibrium. So there's like unstable equilibrium, which is where even a tiny change to what's going on could just drive you out of equilibrium. You can have a stable equilibrium if everything remains in equilibrium, even if you change the forces, at least for some range of parameters. And then metastable is somewhere in between. So it's a bit arguable, to what extent is anything ever really in stable equilibrium? Almost anything is secretly in metastable equilibrium, where metastable just means that it's in equilibrium. You change the forces a little bit, it will stay in equilibrium. If you change them a lot, then it won't be in equilibrium. So really, the two cases that actually occur in physical situations, that is real situations, are the first one and the last one, and this middle one is kind of an imaginary situation. So really, you want buildings and bridges to be in a very good metastable equilibrium. You'll see what I mean in a second. Before that, okay, you drag yourself here on Wednesday when the weather is amazingly nice. So I want to try to reward you by giving you a very simple chime-in. Okay. So this is about force stripping. Okay, it's about equilibrium, and no calculations are needed. Okay. So we have a truck, which is pulling a horse trailer. You can see here what is obviously thoroughbred horse. There is hay, never mind what that is, and I leave it to your imaginations. And you have three different choices, okay, for attaching a cable between your horses or us truck and the horse trailer. And your goal, to be clear, you're a nice person, you're kind to animals, so you want the horse to have a good experience as being transported, not a bad experience, okay? You don't want the hay or whatever else that is to be thrown around, let alone the horse as you go. So to give the horse the best experience, okay, where should you attach the cable? Is it as drawn in C, as drawn in B, or as drawn in A? I'm actually kind of curious what you all think. Okay.
This was like an example choice.
So, all right, I'm just letting folks actually manage the technology involved. Okay. So, well, basically, A is like a really bad idea. Because if you imagine, you have like a really fast horse truck, and you really floor it, okay, you're going to accelerate really fast, and if you pull on the top, basically the whole horse wagon has a chance of tipping over, and that is not a good experience for the horse, right? But if you pull from the bottom, that minimizes that chance. Pulling from the middle is kind of like okay, but like if you really want to minimize the chance, that even if the horse involved is a young horse, it's pretty small, it hangs out most of the time on this end, the C gives the best chance that you're not going to tip over the horse wagon. Okay? We're gonna do something like this, like as an actual work example, probably on Friday. But hold this image in your head until then. Okay. Minus whatever else you want to edit out. So, okay. So hey, let me give you a picture of stable equilibrium. Okay. So imagine an elephant standing on something. Okay. I mean, hopefully, assume the elephant is a rigid object, which it isn't. But assuming that it's a rigid object, it is an excellent equilibrium. You can push on it, you can try to rotate it. Odds are not much is going to happen. It's just an equilibrium. Now, I have to say, calling it stable equilibrium is, of course, you could argue, right? Because if you get another elephant to push on this elephant, of course you can get it to move. So it's always, like, it's stable with respect to things that a human without machines can do. But maybe not for everything. Unstable equilibrium would be one of these, okay? You have a circus elephant, and you have an audience surrounding circus elephant. You don't want anybody in the audience to sneeze, because if they do, there's a chance the poor elephant will fall off, right? So it's very unstable, but it's in equilibrium. Didn't they have a metastable equilibrium? What happened? I had one. It disappeared. All right, I have no choice. I'm subjected to a drawing. Okay, so here's a, okay, drawing works better if you have something that works. Hold on. Okay. Table. We have a plank. We got a marker that actually works properly. Okay, so can I draw an elephant? Here's the body of the elephant, legs of the elephant, head, ears, trunk. Oh no, the tail. That's an elephant, okay? And then let's say there's a person. Okay, so the elephant is in excellent equilibrium right now, right? But if you imagine this board being very long, you know, for small motions of this person, everything is going to be okay. But if you can go out far enough, at some point you could flip the elephant over. Now they're endangered, so we shouldn't do that. But like, what's the problem, right? Because you see, the problem is going to be if the board starts rotating around this point. That would be a real problem. The thing is, the elephant produces an enormous downforce over here. And that gives you a huge torque this way, but the size of that torque is just fixed once and for all by the mass of the elephant in this distance. Let me call this, I don't know, X elephant, right? So we have M, G, X elephant. That's it, right? That's the torque due to the elephant. And then the person also produces a torque. Okay, so this is X person, and then we have M person. So the torque due to the person is M person times G times X person. Well, I mean, this is just fixed once and for all. Let's say the elephant isn't moving, but if you start going this way, even though the person's mass is small, at some point the X will start winning, right? Because the person wants to go this way, the person wants, so basically it'd be a bad day for everybody involved if the person won, right? Because then everybody would flip over. But if you go out far enough, you'll get the thing to flip. So this is definitely not stable equilibrium. It's like metastable. A big enough change to what's going on, a big enough change to the torques will definitely make the system unstable. I meant to have a slide with all of this, but I was editing this before the lecture, and I must have done something terrible to it by accident, so I'm so sorry. Questions, comments, concerns about the elephant? No? Okay. So, all right. So let's do an example, okay? So let's say you have a suspension bridge. Okay, some of you are like future civil engineers and mechanical engineers. So you're going to be doing things like this. My condolences. Let's say you have a suspension bridge, and there could be a truck that could drive onto the suspension bridge. And you might want to know what is the tension in the vertical ropes that are holding up a particular segment of the bridge. Okay? So, well, this is like a big question. To make it precise, we should label the picture somehow. So, let's do that. Okay? So, I'm going to redraw everything in a second, so maybe I should just do it right now. Let's see. So we have the bridge. Okay, there's a segment of bridge being held up by two vertical ropes that are themselves attached to something, but never mind that. Now, bridges are heavy, right? So if you have a chunk of bridge that's held up by ropes, you cannot neglect the mass of the bridge. It's probably pretty big. So let's say that the mass of the bridge is MB. And let's say that the length of a chunk of bridge is L. This is L. And MB is the mass of that thing. And let's say that it's a uniform object. So, by the way, like one reason that in architecture, in engineering, typically you build something out of relatively simple looking uniform pieces is because it's easier, because then the calculations are easy. You could do it with complicated shapes. That's what architects tend to want, because it looks really nice and it has many advantages maybe. But like the calculations get really painful if something has a complicated shape and mass distribution. If it's a nice simple thing, it's easier. Okay, so, and then let's say that there is a truck, which I'm going to represent as a blob. So this is something with a mass mt, and it could be a distance x from the end of the bridge segment. Now, of course, x can vary, okay? We're going to think about what happens as a function of x. But our question now is, there's a tension here. There's some tension there. They're generally not going to be the same. So that's what we want to know. We want to know what is T1 and what is T2. Does the question make sense? It might be terrifying to contemplate actually solving the problem, but does the question make sense? Okay. So, what we need to do now, and what is true in most of these problems, is that they benefit from getting drawn multiple times. Once to understand the problem statement, that's what I just did. Second time, to draw a cleaner version with all the forces, so a free body diagram. So let's do it. There is T1, there is T2. Here is M truck times G. And what else we got? Oh yeah, the mass of the bridge points down too, right? It gives you a force down. So that's all the forces. And I drew them roughly where they're being applied. You buy that? So we're going to draw this one more time later. Okay, but first we're in a position to write out equations that follow from imposing cancellation of all the forces. Because we want all the forces to cancel. So let's write that out. So first, vertical forces. So, well, they're all vertical forces, so this, this is really easy. Okay, so T1 plus T2 minus MBG minus MTG, they have to cancel, so you have to get 0. Right? Like, if that doesn't happen, then the bridge will just fall or go up. Neither of which is a good thing from an engineering perspective. Okay. Fine. And then the next thing that we might want to do is to see what torque tells us. So torque. So for torque, we have to decide two things. First, what's the axis that we're going to use to define our torques in the first place? And second, which direction is positive? What the hell? Oh, hold on. I don't remember what I did. So, and then the next slide is uninformative. This is embarrassing. Okay, so let me just do it in real time, okay? And let's see if we get the same answer, because it shouldn't matter. So, okay. So here's my thought process looking at this, okay? I can choose the axis to be at the place where one of the unknowns is living, because then, if I put the axis either here or here, then either this thing or that thing just won't contribute to torque, which means my torque equation will only have one unknown. Okay, this is going to make my life easier. And then the other thing is, somebody in the problem statement told me that this distance is x, and this distance, like overall, is L over 2. So it's just easier to make this the axis. It reduces how many calculations I have to do. So I'm going to do that, okay? So I'm going to say that for my purposes of the torque, okay, this is my axis, and I mean, what the hell? Let's say like this is positive. Okay, that's a positive torque. All right? So, okay, very good. So let's look at this. So let's go in order, starting from here and then go in. Right, so this thing pulls me up, so it's a positive torque. And, well, how big is it? T1. It is a distance L away from my axis. And it's at 90 degrees, right? This angle here is 90 degrees. So, sine of 90 degrees, but this is just 1. So I'm not going to keep writing it. It's going to be the same one everywhere. Okay. Plus everybody else, right? So this thing and that thing. But see, this one is down, so it tries to pull me opposite to what inside it is plus. So I should write it as minus m b g times L over 2. The angle is 90 degrees again, so that's just 1. The sine of 90 degrees is 1. And then another minus mtg times x. And okay, and then all of that is 0. Okay? So, this is not so bad, right? Because now, look at what we can do. What I can do is I can solve this for T1, this equation right here. Because this is 1, so I divide everything by L, and I just isolate T1. So T1 is equal to MBG divided by 2L. Nope. Nope. There we go. Minus MTGX over L. Nope, plus, I cannot do arithmetic, sorry. Okay, after all of those corrections, does anybody have concerns about what I wrote? Do you see where it came from? Is it correct? Please don't hesitate to call me an idiot politely, if indeed I am, because that happens all the time. Okay. All right, we got T1. So what do I mean by this, in saying that we got T1? I mean, if somebody told us the mass of the bridge and the mass of the truck, and they told us X, and the length of the bridge, like, we're done. We know the tension on one side. So now, what about T2? Well, we have this equation, right? So we can solve this for T2 in terms of T1. So T2 is equal to MBG plus MTG minus T1. Well, T1 is over there. So okay, I just copied stuff. And so now this could be simplified further if you want, okay? But we're set, okay? So you see there's two things here with MB, you could pull them together. There's two things with MT, you could pull them together. This is not very exciting, it's just math. So we just solve for the tensions. So I think this is all consistent with what I did before, okay? Let me just do a quick sanity check. T1, okay, that's the same, right? And then this thing, that part's the same, that part's the same. Yeah, it works. Okay, so at least it's consistent with what I did before. I have no idea where I chose the, oh, I even did the same thing, pick the right endpoint of the bridge. Okay, so yesterday's version of me was the same as today's version of me in choosing where the axis is. You're gonna get these slides, okay? So what do we learn from this? Well, there are two special cases, right? So basically, if the truck is in the middle, then you're sort of, that's the best case scenario, because some of the extra weight tension due to the truck is here, some of it is there, but it's evenly shared. But if you're designing a bridge and you want to make sure these cables are strong enough, then you want these cables to sustain the maximum possible tension. But so if you know that the maximum possible tension comes from having, like, well, let's say you know there's only one truck that ever goes across the bridge, just for the sake of argument. Then if the truck is here, the tension T2 will be maximum. So let's see. That should be possible to see. But sometimes I'm very slow. Sorry, I'm trying to decode what the heck I was saying before. I mean, what I did before is I took these general formulas that I had and I plugged in the two special cases, x equals 0 and x equals L. And when you do this, like what the tensions are, basically like flip between T1 and T2. But you gotta make sure that the tension, the braking tension in the cable is not less than, say, this value. Okay? That's not the point of this problem. The point of this problem is, like, can you figure out what is the static equilibrium condition for this particular setup? If you're given the information about, like, okay, it's held up like this, there's a truck, it's X distance away from one of the ends. This is not as hard as some problems with static equilibrium, and it's within the range of what I would consider, with some intermediate step guidance, to be doable in an exam. You have any questions? Yes?
So I was just wondering what happens to the normal force of the truck, because like, we're not accounting for it, but there's still normal force.
Good. So your question was, what about normal forces and stuff? So what we're thinking about here is the force that is on this object. So we're drawing a free body diagram for this thing, and using that to figure out the tensions. But it is true that this thing is also pushing on that. But that's not part of the same free body diagram. In other words, that normal force, so if the truck pushes down with some force, then this thing has to push up with the equal and opposite force. That's just taken care of automatically from the statement that the truck is not falling through the thing. But we don't have to worry about it for this kind of thing. We just have to worry about the forces on the object that we're contemplating rotating or moving. I don't know if that helps you. Maybe? Okay, so on that note, I hope you can enjoy the rest of the afternoon. I hope it doesn't start raining.